During this fourth module, we are going into more details on the properties of electromagnetic interactions. In this second video, electromagnetic scattering is analyzed in terms of invariant amplitude and cross-section. After following this video, you will know Fermi's golden rule, the scattering amplitude of a particle in an electromagnetic potential, how the target particle generates this potential, and the difference between distinguishable and undistinguishable processes. In the previous video, we have seen how the cross-section for a scattering process is measured by normalizing the reaction rate by the luminosity. For one incoming projectile on a single target particle, the cross-section is also a calculable quantity. The main ingredient is again the probability that both interact by exchanging an intermediate gauge boson. This probability, or rather its amplitude, is calculable in a quantum field theory based on a gauge principle. One can thus compare experiment and theory with good precision for both. Such comparison can test the theory and determine its parameters like masses and coupling constants. The prescription for the calculation of a cross-section is called the Fermi's golden rule. In the scattering theory, the reaction rate W is given as the product between the modulus of m squared times q, with the invariant scattering amplitude m and the density of final state q. The latter is also called the phase space factor. It takes into account the number of states in the quantum sense that the final state may contain. The more there are, the more probable the reaction becomes. For a four-body reaction A plus B, which goes in C plus D, the amplitude m can be interpreted as the probability amplitude of the process that converts the initial state into the final state. It is therefore a probability amplitude in the same sense as the wave function, and the square is a probability density. To obtain the cross-section, we still have to normalize by the flux of incident projectiles. This may seem surprising for a single projectile, but the flux is the number of projectiles per second and per unit surface. Here is then the Fermi's golden rule for cross-sections. It is obtained by properly normalizing the probability of the reaction and contains both this probability, modulus m squared, the incoming flux F, and the phase space factor Q. The incident flux for the initial state depends on the relative velocity, the modulus of VA minus VB, and the volume density of projectile and target. This volume density must be proportional to the energy of the two particles to be relativistically invariant. In our normalization, this is simply equal to twice the energy for a single particle per unit volume. The second equation is valid for the two velocity VA and VB parallel, and clearly show the invariance of the flux factor under Lorentz transformations. The phase space factor, dq, takes into account the number of states which can be realized by the final states. It contains a delta function that ensures the conservation of the energy momentum, as well as the number of quantum states for all the particles in the final states. The factors of twice the energies again come from the way we normalize the wave functions. How does one proceed to calculate the invariant amplitude? We will outline the argument for the simple case of scalar fields. We imagine that to first order, one local action on the potential Vx transforms the initial states of phi A into the final state of phi C. The probability amplitude of this process, ignoring the normalization factors for the moment, is given by this integral. The argument of the integral is the probability of finding the state phi C at position x at the time t among all states produced by the potential V from the initial state of phi A. The integration over spacetime reflects the fact that this local interaction can occur wherever the potential is present. To help your intuition, imagine that the two-wave function phi and phi c correspond to free particles everywhere except at the place and time where the potential intervenes. The initial state, phi will be a superposition of eigenstates of the free Hamiltonian with the given set of coefficients. The potential will change these coefficients to produce another superposition of eigenstates with a different set of coefficients. The amplitude m is then just the amplitude of the final state phi c, which contains the new mixture. The invariant amplitude m contains all the dynamics of a reaction, thus the whole physics of the type of interaction under study. It therefore follows from the potential operator V. This is the same operator which changes the homogeneous equation of motion into inhomogeneous ones. For electromagnetic interactions, the inhomogeneous equation is derived from the Klein-Gordon equation by the so-called minimal substitution. To extract this potential, we will neglect the terms proportional to E squared, which are much smaller than 1. The invariant amplitude is then given by an integral over the product of the 4 potential A mu of the target and the current density J mu of the projectile. The invariant amplitude of electromagnetic scattering of a fixed target is thus the integral over the product between the transition current of the projectile and the electromagnetic potential of the target. Note that this is a local interaction. Current and potential are defined at the same point in space-time, but this point may be anywhere. Thus, an integral over space-time gives us the total amplitude. The electromagnetic current density at work here looks like that for a free particle, except that the fields in the initial and final states are not the same, since there was an interaction. So the electromagnetic current density interacts locally with the potential A mu, which we identify with the photon field. It remains to be understood how this potential is generated, that is, how the photon is produced. For electromagnetic interaction, the Maxwell equation tells us how the electromagnetic fields are produced by charges and currents. Let us start by writing down the homogeneous Maxwell equation in 4-vector form using the electromagnetic field tensor F mu nu. Translated into equation for the potential, this gives 4 differential equations for the 4 potential A mu. Using the invariance of the potential under gauge transformation with an arbitrary scalar field xc, we can always arrange things such that A mu has no divergence. We call this arrangement the Lorentz gauge. In this gauge, the homogeneous Maxwell equations are nothing else than 4 Klein-Gordon equations for the components of the potential. But only 3 components are independent of each other because of the gauge condition. This justifies that we consider the homogeneous Maxwell equations as the equation of motion for the photon, which is a vector boson and thus has 3 independent components. In the presence of a current, the equations become inhomogeneous. There is a source term J nu on the right. We construct J nu from the wave function of the 2 other partners in the reaction, the target particle B and its final state D. Their transition current is the source of the field. The potential A mu that corresponds to this situation is proportional to this current density and inversely proportional to the square of the transferred momentum Q. The invariant amplitude thus corresponds to the interaction between 2 currents. The intervening factor 1 over Q squared is called the photon propagator. It describes the probability amplitude that a photon with 4 momentum Q is exchanged between the 2 currents. Since each current density brings in a factor of V as a coupling constant, the amplitude is proportional to E squared over Q squared. This process can be represented by a Feynman diagram, as shown in this slide. These diagrams describe elementary processes in a manner that is both elegant and intuitive. If the construction of the Feynman diagram for a given process is still a problem for you, please go back to the optional video 4.1a. At the same time, Feynman diagrams are a prescription for the corresponding invariant amplitude. The vertices are characterized by a coupling constant, the electric charge in the case of electromagnetic interactions, and an operator which describes the properties of the interactions. The lines correspond to propagators of the particles, real ones for external lines, virtual ones for internal lines connecting two vertices. The propagator 1 over q square we found for the virtual photon is a special case for the more general one, which is 1 over q square minus the square of the mass for massive intermediate vector bosons. If more than one elementary process can cause a reaction, we must either add the amplitudes or cross-sections. Because of the quantum nature of the processes, there exist two cases. If initial and final states of the processes are indistinguishable, one must add the amplitudes. If there is an observable which allows in principle to distinguish different contributions, no matter if they are actually measured or not, these sub-processes are distinguishable and one must then sum the cross-sections. The first case occurs, for example, if one considers two contributions of different order in the coupling constant. The exchange of one or two photons can intervene between the same initial and final state, as shown in the picture in the left. If the two amplitudes m1 and m2 describe the two contributions, the square total amplitude, which leads to the cross-section, is then the modules of m1 square plus m2 square plus twice the product between m1 and m2. So this last term is an interference term which appears in the probability. This is precisely not the case if the processes are distinguishable in principle. Take the example of different spin direction of the particles that interact. These are observable in principle, as shown as in the example shown in the right. In an unpolarized initial state, they correspond to a mixture of all possible spin orientation in equal proportion. We must therefore average the cross-section or the square amplitude over the spin direction of the initial particles to calculate the cross-section for an unpolarized initial state. If one does not distinguish the polarization of particles in the final state either, one must sum the cross-section corresponding to the spin direction of the final state particles. The square of the amplitude resulting from both operations, averaging over initial spin and summing over final spin, is denoted by modulus m square bar. In the next video, we'll discuss fermion spin and its consequences in more depth.